component. And in the app, you could choose each of these. For this particular example, we've got some of our field lines that look like this, and now we're going to say, okay, let's plot the Vx. And you also have to, when you do this, you have to make a distinction about, okay, what do I mean by positive? And in this case, you could say, well, positive means it's going to be pointing in the x direction, the positive x direction, which in this case is north. Okay, so you always have to define a coordinate system so that you can decide, okay, am I going to plot this thing positive or negative? If I go ahead and I do this, I look at this quantity here, and he is pointing in that positive direction. He's pointing in that positive direction, and so therefore it's going to be a positive value. Similarly, even a point out here, still pointing, the x component is still in this way, so it's still up here, and similar down here. And then when you get really far out, so if you're way out here, now the magnetic field lines are going to be pointing down, and so you might get some kind of negative. So you might expect to see something that looks like that. So that's going to be your signature for the horizontal component that's above there. So you can just play around with the app. So here you've got the app. You can make, in this case, we've got an inclination of 0 and a declination of 0. And if we go ahead and we look at what the north-south profile is, so here's the x component, and we want to do a north-south component profile, then we actually get up something then that okay, so that's the magnetic. Let me now go to some essential items. So what I want to do today is kind of summarize some of the important points. So did anybody catch the mistake I just made? Okay. So I drew the magnetization like that. So which way should those fields have gone? Ah. It should go that way, right? So the magnetic fields go out like this. Yeah, no. And now, if I plotted the x component, what would I have got? So now it's in the opposite direction. So that meant that the sign was wrong. So I actually get something that is like this. And if we look at the app, we see that it goes like this. So here's exactly how you do things. Go along, sketch something out, plot some lines, take a, see what you get for your anomalous signal on a profile, then you go back and check on the app. And when we did that back here, we noticed that, oh, wait a minute, we had a positive polarity. Maybe there's something wrong. So then you go back and you look and say, oh, yeah, I did this or that. And then you eventually end up with something that looks like this that matches what you've got up here. And you're good to go. Okay, so that's the process. You've got a total field here, X component, Y component, Z component, and there's also a gradient. I haven't talked about that. But just experiment, just keep trying these things until eventually you get them done. Then once you've got it, as I said, you're good. Okay. So what I want to do now is to pick up a few of the things that were important, both in the field, especially in the field, that had to do with doing the base station removal, as well as there is an example that it's kind of fun to do. If we can ever get some time, we're going to do. I'm going to pin some magnets down underneath the table, and you can use your cell phones and you can try to find them, and that actually scales up really nicely to try and find a big mineral deposit. Look at that. The first thing I want to talk about here seriously is remnant magnetization. So we talked about that at the beach, and the idea is that if you have temperatures of a rock that are really quite high, so then the little domains inside the rock, all the little magnets are just sort of flip-flopping all over the place. There's too much thermal agitation. So there is no net magnetization, even though the magnetic field of the Earth is coming down like that. As things cool, if you get below this point here, this critical point called the Curie temperature, then the domains lock in on the direction of the Earth's field, and as that then cools, then they stay fixed. So that's how the whole process works. Take something that's really hot and magnetic, put it inside a magnetic field, and then it's going to capture the magnetization that existed at the time it cooled through its Curie temperature. So this direction, of course, can be completely arbitrary. Some of the steel objects that you had out in the beach, they're done in some foundry, and so who knows which direction your steel is in. There's all kinds of randomness that goes on. But the bottom line is that if I'm sitting at some place on the Earth, and here's my magnetic field coming in, so now I've got an object, and it's got a magnetization that looks like this, and we're going to call this M sub I being induced. That object could, however, have some remnant magnetization. Picked it up somehow, and maybe that's in some different orientation, and it's going to be called MR. So these are both, so this is the remnant magnetization, so that's a vector. Induced magnetization, that's a vector. The total magnetization is going to be the sum of these two guys. So it's like this thing. So here is the total magnetization. So it's also a vector, and it's pointing in some particular direction. So the process is that they basically found there's sort of two independent contributions to their magnetization. On a large scale, if you go down into the Earth, progressively heat up, I'm sure you're aware, and there's this temperature kind of boundary, here's sort of 550-degree mark, and at that point here, you no longer have any net magnetization. Everything is completely above the Curie temperature. This has got some implications for larger scale investigations, because it means you're only going to be able to see down a certain depth. With a magnetic survey, for instance, even though you're covering maybe all of BC, you're not going to see down greater than at most 20 kilometers. Places that you're encountered magnetism or magnetization, unexploded ordnances, something like the things that you saw down the beach, or seafloor spreading. So here's the oceanic floor spreading out. So as the lava comes out, it's all magnetized, or it's got magnetic particles in it. As it cools, it acquires the direction, magnetization in the direction of the Earth's field. And then the Earth's field, as you know, flip-flops. It does polar reversals, so that what's at the North Pole eventually becomes flipped over to the South Pole, and vice versa. And that happens every sort of million years or so, and then that gives rise to a magnetic stripe anomaly that looks like this. So if you went over here with, in fact, with that same instrument that you took out yesterday, proton precession magnetometer, and you went across on over the ocean floor just off of British Columbia, so this is the Juan Fuca Strait, then you'd see bands of magnetism that magnetic field that look like. And North America, complex structure looks like that. So that's the total magnetic field map of North America. And some of this stuff was induced, but some of it is just remnantly magnetized. We have an app that you can use. It allows you to put remnants in. You'll use it in the lab next week. I won't go through that at this point. Okay, so what instrument do we use to measure if we have a survey? Well, the question is, first of all, if we have a survey, what are we looking for? Are we looking for, the existence of a big object? Are we looking for some detail? Are we looking for, some features? All of these things are important elements of your whatever survey you've got, and kind of depending upon that, there's a question about what instrument should I use? Should I use a total field magnetometer? Should I use something else? So just to give you an idea of what your options are, the first is there's a proton precession magnetometer. That's what you used yesterday, and basically what this does. Like water molecules have got a spin to them. They've got protons that are spinning on their axis. And so they're like little magnets. If I put in a big magnet, that's going to torque those guys over. Okay? And then if I reduce that external field, these magnets kind of relax back to their initial position. But in doing so, they preset, just like a top. Remember, if you take a top and you spin it and you try to apply a little bit of a force, if this thing goes, kind of goes around in a circle, it precesses. So you can measure that rotation of precession, and then that actually is related to the magnetic field. So that's kind of the thing that you have. Basically, the thing that you had out yesterday was a water bottle with a coil around it. So, and that actually generated, it activated proteins or protons to give you your signal. The other kind of a system that you have, and this is what's flown up in various satellites, it's also in magnetic observatories, is something called a flux gate magnetometer, and sometimes they can also make these into SQUIDs, so superconducting quantum interference devices. And they will actually measure 3 independent components to it. So you'll probably hear this word flux gate, and you'll probably hear proton precession or cesium vapor magnetometer. So these 2 things measure the total field, and this measures the individual component. They come in a variety of shapes and sizes. We've already seen one on your iPhone. You can put them in little devices and put them into the sea. You can fly them in a helicopter. Here's a boom with a magnetometer on front. Sometimes you want to find the gradient. So by gradient, we mean the change between here and here. So I'm looking at the difference. So that's what these guys are. So here's a magnetometer here, here's a magnetometer here, and then there's one back. So you can get all kinds of like the change in the magnetic field between these 2 points. So that's useful. This one's really instrument. It's got a lot going for it. A lot of satellites, virtually all satellites, have got a magnetometer that's associated with it. This guy here he's doing a gradient measurement from looking at the difference between the top and the bottom. I'll talk a little bit more about that, but anytime you're looking at gradient, you're looking for changes in the field, and those changes will be most rapidly occur if I'm actually pretty close to the source. Archaeology experiments or something like that, where you're looking for something that's really near surface, often have magnetometers. So a variety of instruments. Some of them CNT vapor, some total field magnetometers, some instruments. So how are you going to set up your survey? It kind of depends on what you're looking for. When you were doing your survey on the beach yesterday, the day before, you were actually given a lot of predetermined information, because there was already a tape measure out here, and you were told that, yeah, someplace in here there's a piece of rebar. So that's fine. How are you going to try to find this? Well, you don't know where it is, so you just got a sample. And generally, most efficient way is to first of all decide, okay, I'm just going to sample at a uniform rate here, okay, across. That's fine. But then the next thing is, well, what should these be? 10 centimeters, 20 centimeters, 50 centimeters. All of those things will make a big difference, because you saw how much time it took you just to get a single measurement, and also because you're repeating. So how do you make some progress in here? Well, the only way you can do it is to have some idea about what signal you're looking for. Now, if I have a rod, okay, that's buried, let's say 1 meter deep, and I'm sitting up here with my sensor, I suppose I'm just kind of going along here, then because this is 1 meter deep, I'm going to have some kind of a signal. Let's suppose I've got a total field magnetometer, and my signal is going to look like this, where this scale length, you can think about that half-width rule I used. You're not going to be so far out. So this half-width might be in the order of the depth of burial, or if I'm sitting up here, so suppose this is 2 meters high, that's what that was. So now you're 2 meters plus 1 meter, you're 3 meters away from this guy. This thickness here is probably about 3 meters. That's that kind of half rule. And now if you want to capture this, you need to have a certain number of points, right? Maybe 3 or 4 points per half width. So that's kind of the thing that you're going to go on. You have to have some idea about what the signal is that you're looking for. So that means you need to know something about maybe the depth of burial or the range. And then you want to orchestrate your data acquisition so that you're sampling often enough that you've got a nice representation of this curve. Okay? That's in 1D. If you're in 2D, then now it's a little bit more complicated, especially if you're looking for a small, let's say a small object in here, and you don't know where it is. So now this is representative of the rebar that was done, because you had about 10 meters on one side, and you have no idea where it is. So if you're going to do a geophysical experiment over top of that, there's no preferential direction, east or north or south, so you probably just lay out a grid, right? And go ahead and sample on this grid. That would be a very reasonable thing to do. And then the question is, well, what is my delta X or what is my delta Y? Again, you have to have some idea about how deep the object is and what kind of a signature it's going to be, and then you're going to have to make sure that you capture a representative number of points so that you can actually see this. An anomaly that is characterized like this, boom, a single point, I mean, maybe I believe was the rebar, but you can also get just wrong data that come up, in which case that's not your solution. So if you see something like this, then you at least want to have some more points, and then you gradually build it up. And that actually is what happened when you went up with the experiment, right? Because the first team would do 3 points, and the next team did 3 points, and then you start to put those in, and then gradually you find like, oh, that's interesting, something's going on here, and then maybe I'll sample around a bit more closely. So I think the things that you kind of picked up at the beach sort of feel kind of intuitive with respect to what you have here. But the bottom line is twofold. One is you've got to have some idea about the signature that you're looking for, and that's going to depend on the depth of area. The deeper the object is, broader scale it is. So the most difficult targets to reach or to see are the ones that are just right at the surface. Imagine that you had a total field magnetometer and you got an object that's sitting, at 1 centimeter below the surface, and now you've got a magnetometer that's going 1 centimeter above the surface. And the magnetometer is like this, where this is maybe 4 centimeters. So if you try to even go every 20 centimeters, it's like, whoa, dude, I'm gonna miss it, right? So you miss it. So that could be really hard. However, there's a simple solution to this, and that is like, well, let's not measure right at the surface, let's measure up top here. So let's go up a couple of meters, which is exactly why that thing is on the pole. So now, because I'm up 2 meters, even though this thing is at the surface, the anomaly, is a couple of meters wide. So it's lower altitude, but it's broad, so I can see it. Okay, so all of those things, that's what plays into your whole role of doing that survey design. You've got to know what you're looking for, and you have to be able to decide, I'm going to sample this, and I'm going to have enough points that I can get my anomaly. Do that. Good job. When you're acquiring data, especially in an aircraft, you probably fly like this. You go up this way, look around, and you have what's called a line spacing, which is kind of self-obvious, the distance between lines. And then you've got a station spacing along here. So very often on airborne surveys, your station spacing might be 10 meters or something like that, but your line spacing might be a couple 100 meters or maybe a couple of kilometers. So processing. There's a couple of important things. There's two that are crucial. One is to remove the time variations of the Earth's field. So we talked briefly about that at the beach, and this is why you have a base station. And the other is to remove a regional trend. So I just want to take you through both of those. So let's think about time variations. If you sit up here with a magnetometer, one that's a little bit more sensitive than on your iPhone, you find that as a function of time, okay, we've got a magnetic field that looks like this. So these numbers are nanoteslas, so this is 51,300, this is 51,370, and this is 24 hours, and you can see it's fluctuating by 50 nanoteslas. That's at a moderately short time, 48 hours. You can also have bigger events. These are called magnetic storms, and they might be hundreds or thousands of nanoteslas. So you'd be fairly quiet, and then suddenly you get this great big solar eruption on the sun, and then all these particles come out and interact with our magnetosphere, and then they just really cause havoc. So those are our magnetic storms. I wanted to say that these external sources can actually come from a whole bunch of regions. They could come from, as I say, the sun, we got solar wind, solar storms, and they can have durations actually anywhere from seconds to months. So they cover quite a wide range. We also have a lot of other things, power lines. Our whole society is just electromagnetically alive, right? We've got currents everywhere, and generate. So that's going to give rise to all kinds of fields. And then the other thing, the other source that's very long term is that there can actually be stuff happening inside here. So in our internal core that's done by the magnetohydrodynamic system to give us our big dipole, which actually has big time variations because on the scale of a million years it actually flips. Right? So here's the that cartoon. This thing that really causes concern. You get all of these particles that get ejected from the sun and they interact with with our magnetosphere. And sometimes, like the sun rotates on a 24-day or 27-day schedule. So sometimes we'll see big storms come by every 27 days. They'll have a particular cycle that's associated. If you want to know what the space weather is like, there's a website that you can use. This can actually be useful for doing some types of planning of surveys. Because the one thing about taking a magnetometer survey is that you can't record good magnetic data if you're in the middle of a magnetic storm. Just stuff is just fluctuating all over. So the other thing about all these magnetic storms is that they give rise to the Aurora. For those people who have had the pleasure of seeing them, here's some images. So you've got particles that are coming down, they're funneling down into the auroral zone, and then the particles excite nitrogen atoms or oxygen atoms, puts them up into a higher elevated state, and then when they decay, they give off the color. So here's a couple of examples. So here we've got lightning. That turns out to be a big source of magnetic fields. And then we've got our infrastructure. This was an example of what things were like in Victoria just a couple of days ago when I took a look. So here's X, Y, and Z, so 3 components. And you can see there's fluctuations that are going on here, in sort of 10, 20, 30 nanometers. So that may be important or may not. If you're looking for an object that's got a a signal of 500 nanoteslas, then these kinds of fluctuations may not be that important. But lots of times we're looking for something that is tens or 20 nanoteslas. And in that case, you need to take into account that. So how do you do that? This is what you did at the beach, right? So you've got 2 sensors, or you could use 1 sensor and keep going back. But you've got, first of all, a base station. So that just records all the time. And generally, this is often what does happen. Instead of just having 1 magnetometer, you have 2. So you take 1 magnetometer, say, okay, that's the base station. That's just going to record the magnetic field as a function of time. And then here you've got your sensor that you're using to record data. So this is your movable sensor, and it records data as a function of time. Yeah, so then you're going to synchronize these times, and then you're going to do a correction by subtracting whatever was happening at the base station from whatever measurement that you have here. So the idea is you're saying that, okay, there's noise coming in, but it's happening like if I'm the remote guy counseling, finding the signal, and Sagi is the base station, then if I subtract, I'm going to assume that, okay, whatever noise is coming in, it's the same Sagi as me. Fair enough. So therefore, if I subtract the value at the base station, I'm now left with just stuff that's happening. So that's a really good way of correcting all of the time. And so you'll do that next week in the lab because you've recorded, you went back to the base station, recorded your values, and then now you'll just plot those up as a time. As a time series, and then you'll use those to subtract from the data, and then that's going to get rid of that time variation. It also gets rid of some general background. So the other thing that is important in most studies is something called removing the regional. What I mean by that, what I mean by that is that when you collect the data, you get something that maybe it looks like this. These numbers here are, maybe 51,000 nanoteslas plus minus, right? So they're big numbers. And as you go, there's, some variation in maybe the background, and then there's also some other signals. So if you look at that diagram, it's like it's a composite of signals, but one has a very long wavelength and one has a very short wavelength. From the point of view of your anomaly, this is the thing that you're likely interested in. So you want to somehow subtract it. So it'd be like this guy here, he's the representation of the thing that you're looking at. Okay? So you somehow want to get rid of this longer, slower decaying thing, and you're going to have to estimate that and then subtract and be left with something like this. And once you're with this, then you can now use like the analysis that we had before, because you're saying, this is just due to some very magnetized body, and that's what. So that's that's actually sometimes a really tough decision to do. I mean, because you could take this curve, and if you tried to draw a dotted line in here, and there's probably quite a few ways that you could actually draw that line. So suppose that suppose I just got a signal that looks like this. So it's kind of going up, okay? And then there's a couple different scales of fluctuations. So what do I want to do for a region? Well, maybe I could just do something like that. That's could be. It's like, okay, I think in general it's sort of trending up. But maybe, maybe the regional is, something like that, right? Either way, if you do that, you're going to get different results and that's going to affect your final. So this estimate of a regional is non-trivial, but is something that you need to contend with. So here's an example. I've shown you this briefly before. This was at Mount Milligan. So here's the magnetic field. So these numbers now probably are making more sense. So this is 56,000 to 65,000. And it's really big up here and lower down here. And it turns out that we're actually interested in an area that's up. So what I want to do is to take this map and somehow estimate the large scale features. You want to estimate that region. Well, one way of, there's a whole bunch of ways that you could do it, but you could think about some low order polynomial or something like that. Subtract. When I do that, okay, so I'm going to estimate this regional. Slides, and here's what I'm going to get. So I estimate this regional, subtract it from this, and now I'm going to look at this little box in here, and this is actually what I see. Now, this particular picture is now informative, because what I'm going to work with here is I'm going to say all the signal here is just kind of coming, it's all my anomalous field, it's just from a buried magnet here or a couple of them over there, and I'm going to use this information to interpret what is actually inside here. So that step of removing the regional was extremely important. So those are the two processes: removing time variations and removing the regional. That's basically it. So now we've got our images. So in fact, here we've got this. In another case, we might have ended up with something like this. So notice now you're starting to. You should be looking at these guys and starting to think, this looks pretty familiar, right? Is that these guys are all just looking like a the total magnetic field anomaly from dipole. Positive on one end, negative on the other. So if you're faced with this kind of a map, you now say, oh yeah, I think there's a whole bunch of dipoles here, so maybe there's some buried metal. In this case, it'd be unexploded ordnances at each of these. There's another interesting thing about this that maybe somebody can glean, and that has to do with the orientation of the colors. Right. So are all those dipoles oriented so that the red is at the north and the blue is at the south? So what must be going on? Remnantly magnetized, right? So this is interesting, right? I take an unexploded ordnance, shove it in the ground. Well, I didn't shove it in the ground, the military did, but so it's in the ground, and it's a small magnetic object that looks just like the signature of a dipole, but the fact that these guys, this guy is reversed compared to him, means that there must be a lot of remnant magnetization going on, which is exactly what happens, because you take an artillery shell, you mold it, you cool it, it acquires whatever field is around at that point, and got some magnetization. So the bottom line here is that here's an example where you could just look at the data image and get some information about what. I want to explore that a bit more, because there's actually 3 ways I'm going to take you through on how you get the information. One is that we could just get it from the images. The other is we're going to interpret it with either a dipole or a monopole. That's how you're going to do your field data. What a direct beach is going to look like a monopole. Or it could be a complex body, and we'll have to use So there's some processing that is typically done to get better images. One of them is called reduction to pole. Anybody intuitively have a guess at what that is? Yeah.
You simplify the object such that it becomes like
Not quite. Anybody else? Remember a fundamental challenge with magnetism and where I am on the Earth's surface. So suppose I'm sitting here, okay? Now, the magnetic field is coming down like this, right? And the object gets magnetized in this direction. And if I look, so now it comes down like this, right? If I look at the total field magnetic anomaly, it looks like this. So the object is here, there's a nice peak up over top of it. Okay? If I look at the total field magnetic anomaly on the equator, however, it's a bit more complicated. Because now my field is coming like this, okay? And if I'm looking at what the projection is in this x direction, okay, we actually had that it was basically something that got a little different, right? So the point is, if I'm here, or if I'm here, or if I'm here, my anomalies are going to look different. So that's a complicating thing, especially when you've got maps. Here as a geologist, got maps from Indonesia, you've got maps from Canada. These things all. So wouldn't it be nice if we could somehow do some magic here and take the data that was recorded any place on the Earth and somehow manipulate it so that it looked like it was a data set that was recorded if the field was vertically down, which would happen if you were at the North Pole. So if you could take the same object and see what it would look like at the North Pole, then you could have a much better understanding of what's going on. So that's the idea with reduction to pole, is that you take data anywhere and you manipulate it so that it looks like that object was magnetized with a vertical magnetic field, and therefore that's the only thing that you do. The other one is upward continuation. And this is going to be the same as if I have taken data at a particular level, but then I wanted to see what would it be like if my data were taken at higher heights. Both of those are actually going to be useful. So, yeah, so let's just talk about this reduction to pole. So here's the example. If I have an inclination of 0, so here's what happens if I record something at the equator. Okay? If I have an inclination of 45 degrees or an inclination of 90 degrees, it looks like this. So here, these are the data maps that successively would be what I'd record if I'm here at the equator, 0 inclination, 45, or 90. So these are 3 data images, but it's the same object. It just happens to be at a different location on the Earth, and you're measuring a different component. So now what we want to do is to perform an operation where we take these data, and it doesn't really matter how we do it. Has anybody here, have you done Fourier transforms? Who has done Fourier transforms? Okay, so that's just 3 words in here. That is a mathematical operation which allows us to take this picture and turn it to this. But how cool is that, right? Because now we're looking at this picture here, and we see, oh, well, that is, clearly the signature of something has just been vertically magnetized. So that operation of going from this to that is called reduction to pole, and I could do the same thing with this map, and I just turn them all into that. So that's a huge simplifying operation, and if you look at virtually any map that crosses a geologist's desk, it's probably going to be reduced to pole. So that's something we should be completely with. Okay. So I'll talk a little bit more about upward continuation next time, but what we're going to do is finish up the interpretation just in terms of being able to look at a magnetic map or magnetic signature, and just to sometimes see what you can glean from geology. So I'll show you some examples of that. The other thing I want to do is talk about representing simple objects in terms of, let's say, monopoles or dipoles or charges. For that, I would really appreciate if by next Friday, there's a section in the GPG that just talks about interpreting in terms of simple objects, and they'll talk about monopoles and dipoles. Please read that, because if you do that, then we can get through that, and then that's also exactly the kind of stuff that you need for the for the lab on next Monday. Because what we're going to do is we're going to, and here's just quickly, so you've got that piece of rebar, and you've got a magnetic field that's coming down. It turns out that that's going to give you just sort of a magnetic charge, just a negative charge. And you know a magnetic charge, a negative charge, has got the magnetic field lines coming in like this. And so you can put all together and decide that, okay, if I get a traverse across here, this is the characteristic signature that I get. But I want you just to read that 2 sections about the magnetic dipoles, and on the app, okay, there is something that allows you to look at the fields from a monopole. Please do that, and everything will be really simple and make sense, and we'll be able to go on. Yeah, the other thing is then there is a short quiz that we'll do on Friday, and that'll be at the end. It'll only take 10 minutes, so we'll do it at the end. So we'll cover all the material, but please read the stuff on the monopoles.